All right, so this is the final exam review for survey of calculus. We want to consider the following three ways of representing a function. And so if you notice here, we have a table. Right here, we have a graph, and we have a formula. We're going to look at these three different representations of a function and use them to describe various things. So in number one, what we start with is the domain and range of these functions. So remember, the domain is the input, and the range is the output. So for the table, on part one, I would describe the domain, which is the input, and the input is always on the left, and the output always comes on the right. So on the left is my domain, so I describe this as a set of things. So the set 0, 1, 2, 3, and 4, because those are my inputs. And then the range R, right, these are the outputs, which are on the right. So my range are the outputs, which are 9, 13, 17, 21, and 25. All right, so that's for the table. Now for the graph, I'm going to assume that the graph ends at these points. I'm telling you that it ends, so I'm going to assume that it ends right here. So for number two, I would say my domain D, right, instead of writing it as a set of discrete things, discrete 0, 1, 2, 3, 4, I'll write it as a continuous interval, and also I'll use interval notation, so I'd say from 0 to 3. Right, the domain, the input, is along the horizontal, and the range is the output, which is along the vertical axis. So R is equal to, then, it goes from 0 down here all the way up to 100. So that's my range. For number 3, right, the formula, right, and I want to figure out my domain for this one. All right, so for this one, it's a little hard to figure it out, so maybe I'll graph it first to try to get an idea. So I'll take out my calculator, and I'll hit y equals, and I'll plug it in. So 3 second e to the 0.05 x. And then I'll make my window, and maybe I'll just make it go from -10 to 10 is fine, why not? Then zoom fit it. All right, so it's going from -10 to 10. And we see what's kind of happening here. So if you want to draw a graph of this, right, it's doing something like that, from -10 to 10. And so my domain, of course, I could have gone from -100 to 100, so my domain actually is going to be, looks like everything and can be put in there, so -infinity to infinity. But my range, I have to be a little bit careful. So on my range, it's obvious here that the function's going to go all the way up, but it looks like it's not going to go all the way down. It looks like it's just approaching on the left there. It's heading towards 0. It's getting smaller and smaller. So one way to represent this is say I start at 0, and then I go all the way up to infinity. Right? So it approaches 0 as I go down, but as I go up, it gets higher and higher and higher. So I could have any number in the output. So that's how I would represent domains and ranges with these three different representations of a function. Okay, so now let's look at the next question. The next question says, number 2, discuss how these functions are changing, increasing, decreasing, concave up, concave down, and the inflection points. All right, so for one, right, what you notice is that f is increasing. Right, so f of x is actually increasing. And it's actually increasing in an interesting way. If you go from 9 to 13, you simply add 4. And if you add 4, you get to 17. If you add 4, you get to 21. If you add 4, you get to 25. So this is actually a linear function. So we know f of x is increasing. And we also know then, and it is neither concave up or concave down, because it is linear. so because so because it is linear. And since there is no change in concavity, it cannot have any inflection point. So since there is no change, let's just abbreviate change in concavity, there are no inflection points. All right, so let's review this again. So f of x is certainly increasing, and it's neither concave or concave up or concave down because it's linear, and a linear function has no concavity. And since there is no change in concavity, there are no inflection points. If we go on and look at the graph in 2, there are several things that we can say about it. So let's take a look at this graph. And first, what we notice is that unlike f of x, right, g of x is not increasing, so g of x is actually decreasing. And it does go from concave down because it's frowning here. Remember, frown down, so it's frowning to a smile to concave up, right? And it goes from concave down to concave up. So what this means, this means there is an inflection point and it occurs at, well, you come up here and you can kind of look. So maybe right in the middle here, so maybe like right about there, there might be an inflection point. So it occurs at, looks like input maybe 1.5, and so 1.5, and the output looks to be about 50. So I can even kind of tell you what it's doing. And then in number 3, right, if we look at the formula, right, the formula doesn't tell me much, but when I graph it, like I've done before, so here's the graph. Let's pull it up over here. You can see what's happening. So now I know, h of x here is increasing, and concave up, right? So and obviously concave up, right? The functions, every part of the function looks like part of a smile, but it's never concave down, right? You can make this go from minus 20 to 20 to minus 10 to 10. You'll see it's never concave down, so it cannot have any inflection points. So you could write something like it is never concave down, comma, so it cannot have any inflection points. Great. All right, so that's number 2. Describing how these functions, in a sense, are changing. So remember, functions can only change in a certain number of ways. They can increase or decrease. The ways they can increase and decrease are rather limited. They can increase in a concave up manner, a concave down manner, or even a linear manner, a straight line. And when they do go from concave up to concave down, you get what are called these inflection points. Let's look at number 3 now. So number 3 are a couple problems involving composition. So remember, once you understand what a function is, then you can combine functions to create new functions. You can actually, there are a finite number of operations that we use. You can add, subtract, multiply, divide, and then the 5th operation is somewhat new to us. It's called composition. You can't compose two numbers, right? So you can't really put a number inside of a number. That's why it's sort of a new operation. But you can put functions inside of functions. And so that's what we're kind of doing here. We're saying, okay, put g inside of f and then evaluate it at 3. So let's do part A. Right, so f composed of g of 3. Right, what does this mean? It means take f of g of 3. Right, so first find g of 3. So here's g. If I go over 3, I go up 0. So this is actually f of 0. And now if I plug 0 into f, if I 0, I get out 9. So this is equal to 9. I can do the same thing with b, and I can just do it. Let's just do it right here. So I have g composed with h evaluated at 0, which is equal to g of h of 0, right, which is equal to g of, so I plug 0 in for x, so I plug 0 into here, so 3e to the 0.05 times 0. This is just equal to g of, and you can plug this into your calculator if you realize that this part here is just 1, and so 3 times 1 is 3. And again, I can find g of 3. If I plug in 3, I get out 0. And so that's equal to 0. And then finally, part C, I want to find g composed with g evaluated at 2. And so this is h of g of 2, which is equal to, well, what's g of 2? Well, here's 2. If I plug it into g, I get out 20. And so this is actually h of 20, which is equal to, so I want to do h, so I come over here to h, and I plug it in for x, 20 in for x. And so I get 3e to the 0.05 times 20. And you'll see on your calculator, if you think about it, 0.05 times 20 is just 1, so it's just 3 times e to the 1. Right, or you can just write 3e. All right, so now on the next question, number 4, it says find the linear function that would be used to model the data in 1 and determine the initial value and slope of this line. There are a number of ways to do this. I'm going to do the rather long way because it uses all the formulas we know. So what we can do, remember, to find the equation of a line, we basically need slope and point. This gives us lots of points, and to find the slope, we just use the rise over the run. So to find the slope, it's this idea of rise over run, or if you like, change in out over change of in. That's what I usually like to say. Or you can be a little bit fancy and say, oh, change in y over change of x. Right? Or not so fancy and just say rise over run. Lots of ways to try to understand slope. But really, you're just taking 13 minus 9, right, the change in the output, so 13 minus 9, divided by the change in the input, 1 minus 0. It's always the final minus the initial, final minus the initial. So on top here I have 4, on bottom I have 1, and so this is equal to, what, just a 4. So slope is 4. I can take any point. I'm going to take the point 0, 9, because it's probably the easiest to work with. And then I put it into slope point form. So y minus y1 equals m times x minus x1. All right, so this is my slope point form, and I simply plug in. So y minus a 9, right? The y value is 9, is equal to 4 all times x minus 0. And so I get y minus 9 equals 4x. And I move over the 9 by adding to both sides. So y is equal to 4x plus 9. Right, so there's the linear function. Right. I could write it as f of x, since it is the function f, 4x plus 9. But you can write it as y equals 4x plus 9. It doesn't matter. And I want to determine the initial value and the slope. All right. Well, the initial value is where I start. And remember, where I start isn't when I plug in 1. It's when I plug in 0. And so you can see from this that the initial value is 9. All right. So my initial value is equal to 9. And my slope is equal to 4, obviously. It's the number in front of x. Right. One way I remember this is I have another form instead of slope point form. I have slope intercept form, which is y equals mx plus b. And so this is sort of in the back of my mind. M is the slope, and b is my initial value. All right, let's look at number 5 now. Number 5 says calculate the average rate of change and average relative rate from 0 to 2 in number 3. All right, so let's start with the average rate of change first. So remember, for this average rate of change, right, so AVG, average rate of change, this is always equal to, you take the change in the output and you divide by the change of the input. So in this case, we're going to go from 0 to 2, so we'll take the change in the output, which is h of 2 minus h of 0, divided by the change in the input, which is 2 minus 0. And so this one is going to be equal to, so I plug in 2 for x, so I get 3e to the 0.05, right, times 2, minus 3e to the 0.05 times 1, all divided by the number 2. And to do this, I'm going to use my calculator, and I'll just round this to 2 decimal places. So over here, move it back. What do I have? Well, I have on the top, I have left parenthesis, let's write 3 second ln, and I have 0.05 times 2, in parenthesis, minus 3 second ln. Right, so I have e to the now, and then I just put 0.05 here. Right, times 1, you get the same. I get the same thing back. In parenthesis, divided by 2, and out pops my answer. And so in this one, you know, what do I get? I get approximately 0.08. Oh, but there's a mistake here. I see the mistake now. I'm supposed to plug in 0, but what did I plug in here? I plugged in 1, so this should actually be a 0, which changes my answer slightly. So how is it going to change my answer? Well, erase this, and I come back here, and I hit second enter, and this term right here where I didn't put the 1, because I'm not supposed to put 1, I'm supposed to put what number? The number 0. Right, so I'm going to put a 0 here, so hit second insert, right, times 0. This will change the answer. All right, so this makes it 0.1577 blah blah blah, which is about 0.16. Okay. The next part is I want to find the average relative rate. All right, so let's write down, how do we find the average relative rate? And the idea of the average relative rate, well, the average rate of change tells me how something's changing, like let's say over a year. So it's changing by, let's say, $0.16 dollars per year. And I want to know, is that a significant change? Right? To figure out if it's a significant change, well, if I'm only making $1 a year, changing by $0.16 dollars per year is significant. But if I'm making $100 a year, you might say, well, 16 cents, a change in 16 cents per year is no big deal. Okay, so that's sort of the idea. How do we understand if this is actually a significant change? And the way that we do this is we take the average rate of change, right? So what we computed just above, average rate of change, and we divide by the initial output. Right, so what that means is you take this 0.16 and divide by the initial, means h of 0, because we're going from 0 to 2. And so this is equal to 0.16 divided by, and h of 0 is 3e, right, e, and we have a 0.05 times 0 there. And so I take out my calculator. I'm going to crunch this number, so let's just take this off of here. And so I'll just take 0.16, and I'm going to divide by left parenthesis 3 second e to the 0.05 times 0, in parenthesis, hit enter, and I get out is to be approximately 0.05, let's do 3, or 5.3%. Right, so I have an increase of 5.3%. Is it significant? Well, I don't know. I mean, is a 5.3% increase significant? I guess if it's you're dealing with overall investments for a year, I mean 5.3% is not terrible, considering the current economic climate. But that's the idea, okay? So 0.16 tells you how it's changing on average. If it's over a year, if X is in years, it tells you how it's changing over that year. And this tells you the percentage change over that year. So average rate of change is this, average relative rate is that idea. Let's look at number 6 now. So on number 6, it says write 3 in the form h of x equals h naught times a to the x, and list the initial value, relative rate, growth factor, and annual percentage rate. Round your answer to 4 decimal places. All right, so the idea is that I can go from this, which is the exponential form really, using the exponential function, and then I can write it as 3 times some number to the x. And the way I find that number, it's actually really simple. It's almost already done for you in a way if you just think about it, right? That number is right here, e to the 0.05. So on my calculator, I can crunch that number, second ln, and put 0.05 in there, hit enter, and out pops my answer. And so my answer becomes, to 3 decimal places, 1.051. All right, so now that I wrote it in this form, what can I do next? Oh, it says 4 decimal places, sorry. So 1.0513. All right, now I want to talk about what is the initial value. And so let's write down here my initial value. Well, that's equal to the 3. Right. One way to remember this is that h naught is the initial value, or the initial value is found when you plug in 0 for x. And if you plug in 0 for x, this becomes 1, and you get back 3. The relative rate, right, or if you want the continuous, right, the continuous rate, these are the same thing. The continuous rate or relative rate is actually this 0.05. Right, so this is actually 0.05. Or if you want, you could also write, if you want to write as a percentage, you'd say 5%. And then what's next? The growth factor. All right, so my growth factor. All right, the idea with these exponential functions in this form, you have a growth or decay factor depending on whether you are growing or decaying. So if you're a growth factor, it's just this number here. It's basically the number you multiply by to get to the next step. And so this one would be 1.0513. And then this also then gives you the annual percentage rate. So the annual percentage rate, what it would be equal to is you ignore the 1 in a sense. The 1 stands for the whole part, and this is actually the percentage growth rate right here. So our annual percentage rate is actually 5.13%. So we haven't talked about this in a while, but the idea is that you have what's this annual percentage growth rate, which is what we normally think of percentage is when we talk about growing. So if I say I grew by 5.13%, I mean I actually grew by 5.13%. But there's another notion of rate, and that's given by the relative rate. And so this is sort of how this function is growing, but growing continuously. Right? So you can grow by a certain percentage over a year. right? I could also recalculate the percentage to figure out how much we grew over 6 months, and how much we're growing in a sense every month or every day, or percentage of how we're growing every minute, every second, and so on. If I do every single instant, that's what this percentage corresponds to. Right, so I could say I'm growing annually at 5.13%, or I could say I'm growing continuously or at a relative rate of 5%. So I think I answered all the questions here. All right. Let's go to the next one. All right, so now number 7, we want to use the table, graph, and formula to estimate f prime of 2, g prime of 2, and h prime of 2. And so there are various ways that we can do this. So let's first take a look at the table, because these are basically 3 problems in one. So I have the table, and to estimate what f prime of 2 is, well, first let's make sure we know what we're dealing with. So here's what we care about. Right, this 2 and 17. And to estimate f prime of 2, what I can do is use the average rate of change between these 2 points and find an estimate for f prime of 2. And I could also do it, though, for these 2 points here. And then I could add those 2 answers together and get a good estimate for f prime of 2. So remember, in this case, the way I remember this is I say derivative, you say rate of change. And if I want to estimate the rate of change, I can use the average rate of change. And so what I do is I say, okay, let's take f of 3 minus f of 2 divided by 3 minus 2. Okay, that's using these 2 values. All right, so first let's do these first. All right, and what do I get here? When I plug in 3, I get 21 minus 17 divided by 1, which is equal to a 4. And then I could do, instead of those 2, I could do the top 2 here. All right, so I do these top 2, which would be f of 2 minus f of 1 divided by 2 minus 1, which would equal, well, f of 2 is 17 minus 13, all divided by 1, which is also 4. And then to get my final answer, if I want to estimate what f prime of 2 is, which is the rate of change at 2, I could use my 2 approximations and add them together and divide by 2. So I get out the number 4. Right, so whatever this is representing, I know that it's changing approximately by 4 each time. And it's linear, so it's kind of obvious, right? It's changing by 4 each time. Let's look at number 2, because it's a little bit harder. So in number 2, what do I have? Let's extend this a bit. So in number 2, again, where am I looking? I want to find g prime of 2, so that's right here. And the idea is I want to figure out what's the rate of change of g at that point. And you can see some things here. Some things are pretty obvious, right? I mean, you can see it's going to be the slope of that little line right there. And so it's not going to be positive. It's going to have to be negative, right? Because it's going down. Right, so slope should be negative. But let's approximate it. So to approximate this, what we can do is approximate, use the average rate change between, basically, let's color code this. We can use the average rate change between these 2 points right here. So we can say, okay, let's take g of 3 minus g of 2 divided by 3 minus 2. And so what's that equal to? Well, if you plug in 3, you get out 0. So g of 3 is 0. Minus, if you plug in 2, you get out 20. And we're dividing by 3 minus 2, which is 1. So we can wind up with a negative 20. Right? Or, instead of using these 2 points, we could use this point and this point. And so we could compute g of 2 minus g of 1 divided by 2 minus 1, which is equal to, so now g of 2 is still 20, minus g of 1, which is height 80. And again, I'm dividing by 1, and so this is equal to a minus 60. And to get my answer, I have 2 possibilities, 2 approximations, negative 20 and negative 60. And so to get a better approximation of g prime of 2, right, which is saying what is the rate of change, how is a function changing at 2, what I can do is add these 2 numbers together, negative 20 plus negative 60, and divide by 2. And so that's equal to negative 40. All right, so every time I seem to increase by 1 unit on the input, I seem to decrease by 40 on the output. Right? And the negative means I'm going down. Right? The positive means I'm going up. All right, and now the last one that we're going to do here, and let's just do it right up here. Right? So for the formula, if I want to find h prime of 2 and you give me a formula, I can actually give you a really nice approximation because I can plug in a point really close to 2. So I could do like something like h of 2.001, let's say, minus h of 2, all divided by 2.001 minus 2. And I can plug this into the formula, so I get 3 e to the 0.05 times 2.001 minus a 3 e to the 0.05 times 2, all divided by this 2.001 minus 2, which we can just write that down, I guess. So what would that be equal to? Right, just divided by 0.001. And I'll use my calculator to crunch this number, so I can take this out, and I'll do a left parenthesis 3 second ln to the 0.05 times 2.001 in parenthesis minus 3 second ln to pull up the e to the button 0.05 times 2 in parenthesis divided by 0.001 and hit enter, and out pops my answer. And let's just round this to 2 decimal places, so this is approximately 0.17. So that should be pretty close to h prime of 2, right, which tells me that the function is going up or down. Well, it's going up because the rate of change is positive. All right, so moving on to the last question. Oh, nope, that's not the last question. So number 8, we still have number 9 left here. So it says, now use your answers to number 7 to estimate f prime of 2.5, g prime of 2, just f of 2.5, g of 2.3, and h of 2.4. Okay, so the idea behind this is if you know the rate of change, then you can estimate what's going to happen in the future, or a point that you're not given. So the idea is like, look, here you have the input 2 and you get out 17. So you know that you have basically start at 17. And then if you know the rate of change, and what we estimated was that f prime of 2 is approximately 4. So we know it's changing by 4. So what we can do is say plus 4 times, right, the change in x. And so we're going from 2 to 2.5, so you'd multiply by 0.5. All right, the formula is over here. The idea is it's f prime of x, in a sense, is equal to, sorry. Let me write this down. All right, so f of basically x plus delta x is equal to, you take f of x plus f prime of x delta x. Right. We never really talked about this formula. Right? We don't really need it. Right? It's just the idea. The idea is this: if you're changing, let's put units on this. This is like $4 per year. Right? So this is in years, and this is in dollars. Right? So if you know you're changing $4 per year, and after the second year you have $17, how many dollars do you have after 2.5 years? Well, you start with $17, plus you know you're gaining $4 a year, but you want to go just a half year, so you have 4 times 0.5. Same thing works for g. So g of 2.3, what is this approximately? Right? This is approximately, well, you start at 2, and so you get out 20. So you get 20. And then plus, right, 2.3, well, how is g changing? Before we found g prime of 2 to equal negative 40. Right, so it's negative 40 times the change in x. So I'm going from 2 to 2.3, and so that's, times 0.3. And so you take out your calculator and you crunch this number, and what you're going to see is that this is actually equal to 8. Right, so 20 plus a negative 40 times 0.3 should give you back 8. And then we can do the same for h of 2.4. All right, what we can do is we can plug in 2 here, because we know we approximated h prime of 2 is approximately 0.17. And so what we can do here, we'd say, oh, this is h of 2, plus, and let's use the notation. So h prime of 2, times my delta x, which is equal to, now h of 2, I have to plug it in, so e to the 0.05 times 2. And then plus this one, let's use the approximation. My derivative, I approximate it to be 0.17 times delta x. So I'm going from 2 to 2.4, so this is times 0.4. Right, so 0.4. I can use my calculator to crunch this. So on my calculator, I'll do 3 second ln 0.05 times 2, in parentheses, plus 0.17 times 0.4. It should spit out an answer of about 3.38. So this is approximately 3.38. So this is basically how you can use the derivative to predict future values of functions. All right, so then the last problem on this first page, number 9, is we want to use the table and graph and formula to estimate these various integrals. All right, so on part 1, how can we use the table to estimate the integral from 0 to 4 of f of x dx? And so there are a number of ways to do this. You could use the left endpoint, the right endpoint, or even the midpoint. It doesn't matter. What I'll do is I'll use this left-hand rule, right-hand rule, and I'll average the two together to approximate it. All right? So it's just one way to do it. So the way this works is we can graph it. So let's graph this. So I have 0, 1, 2, 3, and 4. And above 0, I'm at 9. All right, so this is 9. And then at 1, I'm at 13. So here's 13. And then over at 2, I'm at 17. So here's 17. At 3, I'm at 21. So here's 21. And then at 4, I'm at 25. And you can see this actually does create a line. And I'm trying to estimate, in a sense, what this area might be. And the one way to do this would be to use the left-hand rule, or if you want, the left-hand sum. All right, and the way this works is use the left endpoint and go to the next. So there's one rectangle, there's two rectangles, right? Then there's three rectangles, and then there is, here we have 4 rectangles. So what I have to figure out these rectangles, I just want to add up all the various areas. All right, so for the first one, the height is 9 and length is 1, so I have 9 times 1. Plus, then I have 13 times 1, that's this one, plus 17 times 1, plus 21 times 1. And you can put this into your calculator and you should get out 60. Right, that's using the left-hand sum. Or I could use, instead of the left-hand sum, I could use the right-hand sum. All right, so now for the right-hand sum, what can I do? Well, let's draw the picture. Instead of starting on the left-hand side, I start on the right-hand side. So I go back, and I go back and down, go back and down, and go back and down. All right, so now I want to find these areas in blue. All right, so what are these areas? And to do that, I just say, okay, well, this has length 1 and height 13. So I have 13 times 1, plus 17 times 1, plus 21 times 1, plus the final rectangle is 25 times 1. I add all these up and I get 76. And then to get my final answer, all I need to do is I add these together. So to approximate this thing, the integral from 0 to 4, f of x dx, this is going to be approximately 60 plus a 76, all divided by 2. That's 76. And on my calculator, it'll tell me that this is actually equal to 68. Right? Units squared if you want to interpret it as area. And so that's one way to approximate this definite integral using the table. Now, using the graph is really simple. So let's do it right here. So 2. Using the graph, the idea is you count up all these other rectangles here. So each of these rectangles has area 20. So that's 20, that's 20, that's 20, that's 20, and this one's 20. And now we have to be a little bit careful when we add these together. So this region here and here, I bet those two regions add up to 20. And then if you look here, if I put these two together, I bet those are also another 20. And then this one right here in the middle, it's about half of these little rectangles, so it's about 10. So to figure out the integral or estimate the integral from 0 to 3 of g of x dx, the way I would do this is I'd say I have 20. How many times? 1, 2, 3, 4, 5, 6, 7 times. Plus, I have a 10 right there. So if you do that on your calculator, you'll see that's 150. Right, and if you want to emphasize the fact that it's actually area, you can put units squared on there. And that's it. For number 3, the way I would do number 3, since I have a calculator, I would just use my calculator. So let's do number 3 down here. Let's go down a little bit. So on number 3, what I would do is take my calculator and plug in my function, right, because I want to use the formula. Oops, I guess I already had it there. Right, so plug it back in. So I have 3 second ln, so e to the 0.05x. I'd make my window, and since I'm trying to find the integral from 0 to 5, h of x dx, right, what I want to set my window here on my calculator is from 0 to 5, right? So I have 0, 5, and I have h of x dx. Right, so I do from 0, enter, 5, enter, zoom fit it. Right, so I'm going to get a graph, and my graph from 0 to 5 looks something like that. And I'm trying to find this area. And so to do that, I hit second trace. I hit number 7, which is the integral f of x dx. And the lower limit was 0. The upper limit was 5. I'll shade that region in. All right, so here I'm just using this integral of f of x dx button. And it gives me approximately, and let's round this to 2 decimal places, so 17.04. And if you want to emphasize the area part, you'd say units squared. And so that's how you can use these 3 different representations to approximate or estimate area and find these definite integrals.